Hello everybody. I would like to discuss for the next little bit a concept that some people struggle with, other people have no idea how to deal with, and that concept is IPv6 or Internet Protocol version 6. Um, Pop quiz. Does anybody know what the first three versions of the internet were? Time's up. There weren't any. You can do a search for IPv1, you're not going to find anything. There was actually an IPv version 5, but that was all experimental stuff that, like the government and the military or whoever it was that decided, dreamed up another internet version came up with. But IPv6 in itself is the predecessor to, or sorry, the successor to the version 4, um, excuse me, um, addressing standard. Version 6 is going to be one of those concepts that if you don't get it, you're going to struggle with it. Now, it's not a hard concept to understand. It's actually really, really easy once you have a basic understanding of how version 6 works. It's a different convention, as you can see. You got this set up instead of, the 192.168.1.1 with the dotted decimal. The reason that it's different is because of how large of a addressing format that it follows. IP version 4 uses a 4-byte address or 4 octets, or I'm sorry, 8 bytes or 8 bits, 8 bits, 8 bits, 8 bits broken into dotted decimal. Okay? By doing this, it gives you the ability to have 4.3 million? No, I'm sorry, 4.2 billion addresses, I think is what it equals out to. And how you figure that out is in each octet you have 0 through 255 equaling 256. So if you were to multiply 256, so a 256 here, here, and here, you get 16.7 million addresses to here. I think it's 4.2 billion right here for the entire, all four connected, or all four U's, you get 4.2 billion addresses. Well, you might think, well, that's a lot of addresses. Well, not really. In today's day and age, oh, what did I do? Control Z. That is really not a lot. And unfortunately, with the growth of the internet and other things, it's nowhere near what we need for addressing. So, about 12 years ago or so, and it's debatable exactly when IPv6 was, you know, dreamed up or whatever the case may have been, what the designers of the internet did, and I don't know exactly if it was one person or if it was several, they came up with this new um, protocol to use in order to address the shortage of IPv4 addresses. Well, they came up with some drastically huge address, and this drastically huge address I keep referring to is this guy. Actually, I gotta make my thing a little bigger. I'm gonna go a size bigger. I like it when it's wide. There we go. Now we're talking. So this address right here is a version 6 address typed all the way out. Now, it is hexadecimal, meaning that the numbers 0 through 9 and A through F are valid characters. So that gives you 10, and an A through F is A, B, C, D, E, F. So it's A, 1, B, 2, C, 3, D, 4, E, 5, E, F, 6. So it gives you 16 characters. So 16 possible combinations per digit. Now, I am not super strong on version 6, and I'll be honest with you on that. I have a fundamental understanding of how version 6 works and how to implement it. It's really not that hard. But version 6, now if you really want a stout understanding, you need to get a book on it and really read, or maybe watch some YouTube videos on it. But it is a very in-depth. It can get really, it can get really deep really quick. Now, there's a couple things when it comes to version 6 to version 4. Currently, and this is as of this recording of January 29, 2013, a recent side job of mine required an additional IP address for dedicated secure connectivity to this person's network. Well, the drawback was when I went to call the service provider, who was GoDaddy, to request another IP address at a certain monthly commitment rate, I was told that I could not do that. And when I inquired to their engineer as to why, he told me that they do not allow any more version 4 addresses to be given out because they don't have any. So I'm like, okay, so what do we do? What are my options? He goes, well, I can give you a version 6 address. And I go, okay. And he goes, the only drawback is, like, you're familiar with version 6? I was like, I am. He goes, you have to implement a version 6 routing protocol in your network. You have to be able to NAT between version 6 and version 4. Those are just two issues, because you cannot have a version 4 routing protocol routing version 6. Why is that? Well, the reason behind that is because the version 4 protocols, so OSPF version 3, EIGRP, I think it's V6. These guys don't support, or I'm sorry, version OSPF and EIGRP of the version 4. Lost my train of thought. OSPF and EIGRP of the version 4 routing protocols don't support version 6. So if you're going to implement a version 6 IP address, okay, actually, you have to implement an IPv6 routing protocol. So OSPF version 3, EIGRP version 6, RIP next generation, whatever the case may be. So that's basically what it boils down to. If you're going to run a version 6 address, you have to implement version 6 IP addressing in your network. Now, it's not a really difficult concept to grab, but you have to understand the breakdown to how IPv6 works. Now you see there's colons instead of dotted decimal. So that'll be the first thing that I discuss. Now, the way that you break down a version 6 address is that there's actually 16 bytes of information. So if you take 16 and multiply it by 8, you get 128. So it's 128 bit. And as a matter of fact, I will pull up my calculator. 1 second while I find this. And calculator. My calculator. So we take 16 times 8, 128. So that means that for each one of these, each one of those red lines, actually I should say, is 1 byte. So a byte here, 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 a byte here. You get the gist. So, well, how do you break that down? Well, this guy right here they're broken into nibbles, or half a byte, or 4 bits. So if you got a 2 and a 0 in decimal, or in, I'm sorry, in binary, that is 0, 0, 2, 0. And this guy is 0, 1, and that is 0, 0, 0, 1. So that's what this would equal. Or, well, in this case, it wouldn't be a 2, it would be a 1, because you did turn the 1 bit on, or the 2 bit on, and it would make it a 2. Well, you're saying that's 20. Well, no. If you turn, what is it? All these bits on, it equals F. So if I think it goes, hang on one second. Okay, as you can see, I started drawing out the bits. As you get up to 0 through 15, it would just, the bit combinations would go. Now this is how binary works. So it would be like 0001 would be 1, 0010 would be 2, 0011 would be 3, and this is the bit placement. So this would be the 8 column, this would be the 4 column, this would be the 2 column, this would be the 1 column. So you would, that's how you would break it down. So 20, or 2, would actually be this bit turned on. So this would be the 2 right here. Actually, let me do this. This would be 2 right here, and this guy would be the 1. So this would actually be here, and this guy would be right here. Alright, so that's how that would go. Now if you had a 2 and a 5, it would pretty much, you'd have to 25. Let's see, this, I just put this in here. This isn't always exactly legitimate, but the concept is there. So, like I said, I'm not super strong in this, so it's one of those, I'm just going to play it by ear. Now, I've already explained what is it. It's the next generation of IP addressing. How is it better? Well, it gives you, one second. It gives you somewhere in the range of, oh, what is it? Something like, I have an FTP session right now, and I'm trying to not show you guys too much about what I do in my spare time, but yeah, it's not gonna. You know what I'll do? I'll take a screenshot of this. And what that'll do is it'll this right here is, well, actually you guys can't see that because it's all the way up there. So what I'll do is there we go. This these are the videos that I'm actually downloading from a friend of mine, and what these are, it's network IPv6 multiple IP address types, and it goes through everything when it comes to IPv6, because IPv6 will do the exact same thing that IPv version 4 will do, but at a much larger scale. So you'll be able to do a lot more with it. The beauty, or the drawback to that, is it's a whole nother convention. Meaning you have to get used to another type of setup and stuff like that. So it's going to be more difficult for people to get used to and figure out how to work and stuff like that. So the next question is, how do I make sense of this long address? Well, there's actually it's two 64-bit addresses. So 64 and 60, that's a horrible 4, there we go. 64 is how it's going to break down. So the first half of the address, so right there, will be your subnet. Alright, this will be the network section. Okay, this is the network section of the IP address. And then this back half, this will be the, how can I put it? This will be the device. Well, how does that work? Well, very simple. you're given an IPv6 address to use, and it won't be. I don't exactly know how they're gonna lay it out quite yet, but I know there's 2001 and some change. I think right now they're going 2000, 2001 or 2000 through 3FFF. Whatever this range is, which is probably a couple 100 billion addresses, that's what they currently have allocated right now. Now, they're going to break this into a subnet to where the first 64 bits are going to be unique to your network. And what I mean by your network is the company you're setting this up with. And what you do is you have the 64 bit, the first 64 bits are going to be there's going to be a global IP address, so the 2001 through 3000 FFF, and then you're going to have this would be your global address. Now you're also going to have a unique local, which will be an FE 80 we'll start with, and then you're also going to have a link local. I think I got those right. Maybe FE80 is not link local. You know, let me hop online real quick and check that out. Okay, as you can see, I had to go to my documentation in my CCIE route and switch book, but the first 64 bits, as you can see, you got 3 bits, and you got the prefix. The prefix will be the 2001 address, 2000:/3, and what that'll do is that'll be the first half. Okay, the second half will be the interface ID, so the MAC address of the device you're working with. And what they're going to do is they're going to stick in the middle of right here. So if this was the MAC address, 1111.1111.1111, right here, they're going to stick F, 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 E. Because if MAC address is 48 bits long, they need to make it 64 bits. So they're going to stick in, what's 48 minus 64? 16. They got to stick a 16-bit buffer or padding or whatever you want to call it in here so that they can make it a 64-bit device ID. Now, with that being said, I don't want to go full screen. This is how you turn IPv6 on, is IPv6 unicast routing, and then you would go into the well, it says right here, routers automatically configure a link local IPv6 address on all IPv6 enabled interfaces. However, you can configure the link local address with the following command, this right here. Now, if you were going to, say for instance, set this up, you could type in there EUI -64 does this. Okay. Now, like I said, I'm not an expert in IPv6. That's why I'm really looking forward to this series coming down so that I can watch it. But there's with IPv6, it gets rid of broadcast. You don't have to deal with broadcast anymore because, well, it does away with them. What it does is it replaces broadcasts with multicasts. So it's going to be one-to-many, many-to-many communication. Now, host-to-host communication, 2000, remember that's going to be your global IP address. And then Anycast is the same as unicast, where it's going to be one-to-one. So it's going to go based on, relies on routing metrics to determine the best destination for a particular host. What does that mean? Well, that means Give me 1 second to clear this off, and I'll explain. And a little bit more of this. Beautiful. Now, what was I talking about? Oh yeah, Anycast. Let's say for instance you've got a router here. This is Milwaukee. You got a router here. Chicago. You got a router here. Detroit. You got a router here in say Des Moines. Okay. This being Des Moines, Iowa. Make it better. D. Okay, so you've got these routers. Now they're interconnected. Okay, this guy's connected to that guy, and this guy's connected to this guy, connected here, and then this guy's got a direct connect here. So it's a full mesh internet connection. Okay, you're here in Milwaukee. Okay, so if going based on whatever the metrics are, if you go to eBay, okay, you go to eBay, and you say you want to go to eBay, and you're using a version, eBay is using version 6. So your request comes into the Milwaukee router, and what you want to look for is, let's say Milwaukee doesn't have an eBay server to search from. What it's going to do with Anycast is, because it's coming into the very first router, let's say Milwaukee is your local ISP, so let's say you got Time Warner Cable. It comes into Milwaukee, and actually I live near Milwaukee. It comes into Milwaukee, and Milwaukee says, okay, going based on version 6 Anycast, who has the server web page, or the web address, or the web page that this user is requesting? Well, Detroit says, I have it, and I'm 1,000 miles away. And Des Moines says, oh, I have it too, but I'm only 700 miles away. And Chicago says, I have it, but I'm 100 miles away. Well, it's going to route it to Chicago based on distance. And they all have the same IP address, so we're going to say 1/1. Okay, they're all 1/1. And so it ships it to Chicago. Now, you say, okay, well, Chicago's doing its thing, and let's say, for instance, 50,000 people, 50K, request eBay's webpage. Well, let's say Chicago can't handle that many requests. What it's going to do is it's going to use failover, and it's going to route it to the next closest location, which would be Des Moines. So it starts taking those speeds. Now, Des Moines is getting requests in from other locations, and it's going to give you, the option to, you won't even know what's happening. But Des Moines, the way that the routers will look at it, will be like, okay, well, we've reached, say, 60% of our utilization, so we need you to go to this one. So it'll always go to the best first, then the best second, and the third best third. So it's just like a routing table where you have your entries, and longest match wins. So, well, in this particular situation, shortest path wins. Closest to you wins. That's how Anycast works. Now, multicast, everybody understands multicast. You have one device, and it sends out to another device, and then it sends out to multiple devices, but from the same stream. Now, this is where you get PIM sparse mode. I'll put SM for sparse mode. PIM sparse mode, it sends only when a request is coming. Data is only sent when a request for data is received. Okay, so this will be a rendezvous point, RP, and you're gonna have like a website you're gonna log into, and you're gonna log in or whatever, and click on a video, and it'll start multicasting. So it'll send a single stream to this place, and you might have 3,000 individual users requesting that video. So it'll only send one stream across the internet or across your network to this. Well, version 6 does this as well. or it's one to many. Um, Now you have also thing called PIM dense mode, and PIM, by the way, is protocol independent multicast, which is its own routing protocol, independent of OSPF, EIGRP, BGP, MPLS. So then you have PIM dense mode. So you have this guy right here. He sends out to this guy, and this guy's doing this. Well, this guy's always sending. Okay, he's always sending, constantly sending. So he's got always doing this, but every 3 minutes, what ends up happening is if this guy right here doesn't get anything, doesn't get a request for multicast traffic inbound, doesn't notice anybody coming to him and saying, okay, don't see nothing, he will prune back. He'll cut this connection back to this guy, and this guy goes, okay, no one wants it, so I'll stop. Well, dense mode will keep sending it consistently. It'll keep sending the traffic no matter what happens. So the traffic will keep being sent, and every 3 minutes the connection will get cut. Dense mode. Then there's also called PIM sparse dense mode. So it's PIM S/dense. So when you have PIM sparse dense mode, it does the exact same thing with the protocols are identical, except for the fact that now this is where I get a little confused. I didn't want this to turn into a multicast video, but the concept is still pretty much the same, where it still pushes, and then if there's a multicast address, sparse mode will be in a particular situation. I think that's kind of how it works. But actually, you know what? Let me jump to multicast real quick and make sure I know what I'm talking about. Let me well, anyway, I poked around for a few minutes and I couldn't find it, but I'm not exactly sure where exactly it's configured, but anyway, is it going to be easy to understand with basic explanation? Yes, it will be, and I highly recommend at least reading up on IPv6 because it's going to be something that is widely used and heavily implemented. I don't think it's going to take over the next 2 years, or next 3 years, or maybe the next even 5. But it is out there. It is going to be something that everybody is going to need to know and understand. And eventually it will become one of those things where you're going to want to use it because it's flexible. Very flexible. I mean, you can use now it's still going to have the same NAT thing where you'll be able to NAT from a global address to an inside local and stuff like that. So you're still going to have that. There's still going to be subnetting to do and stuff like that. But for the most part, I really wouldn't worry about it too much. You know, I know it'll work with DNS, but actually I need to go through a refresher course on IPv6 myself. So, but I just wanted to cover the very basics of it. I wasn't trying to like go in depth like I would with some other things like spanning tree or VTP or anything like that. But just a basic overview. You know, I do know that if you are going to have if you're going to run both version 4 and 6 over the same wire, it is called dual stacking. If you're going to take if you're going to be implementing version 6 on your network and you want to route version 6 over version 4, like say for instance you have a VPN set up and you want to route it over that, you need to set up a 6 to 4 tunnel. What else is there that you might need to know? That's all I can think of off the top of my head. Just remember that it's 128 bits long. There is the link local. There is the unique local. And there's the global unicast. So you have your link local, which is the 169.254 equivalency, which is only routable, which is not routable, which has to stay on your local subnet, anything connected to that switch. Unique local is going to be your company. Okay, so your internal, like your 10 network or your 172 network. This guy will be your public IP address. Those are the 3 different types of addresses. I think this is FE80, or, one second. Anywho, I had to go back through some old documentation to figure out what I was missing, and I found what I was looking for. Right here. As you can see, the global unicast ranges will be 2000 to 3 FFF. The unique local will start with FC00. The link local will be the FE80, and the multicast will be FF002::#. The pound sign will be utilizing the same multicast addresses like .10 is EIGRP, .9 is RIP, .6 is all DR and BDR routers, .5 is all OSPF routers. So as long as you can remember those 4, you should be good. So you got, this is OSPF, this is RIP, and this is EIGRP. So remember those. For the .5 is, .6 is DR/BDR. So, like I said, this is the same thing. Link local is the same as this one. FC00 or FC00. FC00. And this one is a global unicast. So, as long as you can remember that, you should have CCNA level understanding of how it works. Now, theoretically speaking, there is a way of being unique when you're setting it up, but if I was you, go watch INE, their CCNA camp, and watch the IPv6 video. It's on YouTube. Check it out, because Brian McGann's a lot better explaining this than I am. So, with that being said, I hope this has been informative for you, and I would like to thank you for viewing. As soon as I find my mouse where I can, there we go. Adios, amigos.